So, guys, let's just start off today by kind of recapping what we have done so far in this chapter 16, this acid-base chapter, okay? We have looked at situations involving strong acids, weak acids, strong bases, weak bases, okay? Your strong acid and strong base calculations are usually very quick, very easy. What is it that makes weak acid and weak base problems a little bit lengthier? Because they require a what? An ice table, you got it, okay? What we're going to do is we're going to talk a little bit more about acids, and then we're going to transition, like make a very different, a big change for the last section of this chapter. We're not finishing the chapter today, but we're going to start the final section today, and it's very different than what we have been looking at. Okay? So, we have seen that term before, polyprotic acids. What is poly, that prefix? What does that mean? Many, multiple. Protic, what does that mean? Protons. Okay, these are acids that have more than one hydrogen to give. And let me give you an example. All right, like carbonic acid is an example, and we can even be more specific because carbonic acid has two hydrogens to give. We can call it diprotic, di meaning two. All right, we could have triprotic acids. And the thing that I need you guys to understand about polyprotic acids, okay, is that they give away their hydrogens. That's what acids do. They give them away one at a time. I need you all to understand that carbonic acid does not give away those two hydrogens all at once. They're given away one at a time in two separate reactions. Okay? And since they're two separate reactions, they have their own Ka values. Okay? Now, there's a vocabulary word, and if you need to go back and look at your previous notes, by all means do that. Let's see if you remember what this word means. There is something on this slide that is amphoteric. Do you remember what it means, Jimin? You got it. It's something that can behave as an acid. It can also behave as a base. It can donate a hydrogen. It can also accept one. What up here, written in orange, what species up there is amphoteric? HCO3 minus, yeah, because HCO3 minus can donate a hydrogen and create just carbonate, or, you know, these reactions are reversible. This polyatomic ion can also accept a hydrogen as well. All right. Now, let's just recap here. Okay, let's do a little review of the thought processes. Carbonic acid, strong or weak? Weak. Perhaps we need to review our strong acids. Okay, this is a weak acid. How do we deal with weak acid calculations? What do we have to do? We have to do an ice table. Okay. Well, this is acting as an acid as well. Is this strong or weak? Weak. Weak acids require an ice table, right? Yeah. Hold on. I can see like the wheels turning in your head. Oh no. No, please no. Are you saying that a calculation with this would require two ice tables? Please say no. Okay. I'm going to make a little compromise. Technically speaking, yes, it would require two ice tables. However, you're not going to have to do that, okay? And I'm going to explain to you why. All right? It says, in calculations, we can normally ignore the second, and if there was a third dissociation, because the first is so much larger, okay? When I say a possible third dissociation, imagine if we had this acid. Okay, phosphoric acid. Wouldn't this acid have not just 2 reactions, but 3? Yeah? Okay. Here's the thing. This relationship is true all the time, no matter what, no exceptions. I don't get to say that very often. All right? The first Ka value for that first dissociation for any polyprotic acid is always going to be greater than the second. And not just greater, guys, like much greater. And if there is a third dissociation, that third Ka value is going to be very, very, very small. Okay, now let me explain why it is that we, calculation-wise, really don't have to worry about this second or possible third dissociation. Think about what these Ka values represent. Guys, these are equilibrium constants, right? Isn't that just products over reactants? Okay? If a Ka value is very, very small, okay, for example, let me just make up a number, like 1.4 times 10 to the negative 9th, let's say. A very, very small Ka value. Think about what that means. Does that mean, is there a lot of product or a little product in the numerator? Very little. That means this reaction is not going in the forward direction much at all. And if this reaction, yes, it's happening, but if it's barely happening, then we really don't need to worry about it for our calculations. And I'm going to prove it to you. Okay? Now, what is on this slide, let me just make a little disclaimer here that this is like just a sneak preview of something that we're going to deal with a lot in our next chapter, in chapter 17. What does the word titration mean? If we're doing a lab and I say, okay, we're doing a titration today, what are we adding? What plus what? Acid plus base. Yeah, it's an acid plus base reaction, which we're going to do a lot of in chapter 17, and we'll do a lab with it as well. If you're doing a titration, and in this particular example, we would have a set amount of acid, and we would be adding progressively more and more base. If we monitored how the pH is affected, we would not see the pH increase in a linear fashion. It takes this sort of S-shaped curve. Don't worry about these terms here. We'll get to that in chapter 17. What I am trying to show you here is that for a monoprotic acid, which is most of the acids we deal with, you will see only one S shape. Diprotic, you will see 2. If we had a triprotic acid, we would see 3. Okay? The point I'm trying to illustrate here is each hydrogen to be donated reacts independently. Okay? In a polyprotic acid, each hydrogen reacts one at a time, not all at once. Okay? But we'll deal with titration curves a lot more in chapter 17. All right? Let's look at a sample problem. Okay? And I'm going to weave in some review from last class. It says, calculate the pH of a solution of 1 molar arsenic acid. All right? This is a triprotic acid, which is why we have 3 Ka values. All right? Arsenic acid, strong or weak? Weak, okay. Weak acids have Ka values, strong acids don't. What we're going to do, all right, is we're going to treat this as a weak acid just like we have a lot of our other weak acid problems. It's an ice table situation. I'm going to help you get it started. Just like all of our other weak acid problems, we're going to react it with water. Now guys, remember, polyprotics, each hydrogen is donated one at a time. So if this is my acid, can you tell me for this first dissociation, what would my conjugate base be in that position right there? H2, very good. H2, ASO4, good, with a minus charge, because we took away one hydrogen ion. And then what's my other product? Hydronium, very good. Okay. Here's what I'd like for you to do. This is the reaction for the first dissociation. You have an initial molarity. You have a Ka value. Please use that information and solve for a pH. Go. All right, how'd you do?
I got the answer.
All right, so here's the situation. We have, at this point, done a calculation of the pH, but we have only carried it through the first dissociation. And we know this is a triprotic acid. There are 2 more dissociations that happen. Okay, now are you going to have to worry about the calculations associated? No. However, you would be expected to predict, to write out the reactions for the second and third dissociation. So let's just practice that. Can you tell me, please? You know, all of these reactions we've written are something plus water. For my second dissociation, what is that something? Okay, very good. Oops. Okay, H2 ASO4 minus plus water yields what? Just H. Okay, H ASO4 minus 2. Good. Plus what? Plus hydronium. Okay. All right. If you were asked to write out the third dissociation reaction, I think you could do it. Now, I just want to show something to you. Okay? I'm going to show you what the calculations would look like. Feel free, if you want to just kind of listen and watch, fine. If you want to write this all down, fine. But you're not going to be doing this. Now, is this a strong acid or a weak acid? It's weak. So we definitely would need an ice table if we were working with it. Just go with me. Okay? Here is the situation, because I want you guys to understand all of this conceptually. This reaction will not happen until this one is complete. So any molarity on the initial line here, where would it be coming from? The final line of the one before it. Okay, so at the end of this first dissociation, you guys tell me, is there any of this? Yeah. How much of it? That much. Okay, we still don't care about water. How about this compound? This compound isn't even in this reaction. So no, there's none of that. However, is there some H3O plus coming from the previous reaction?
Yeah.
Yes, there is. Okay, and from there it would be the same. Minus X, plus X. Okay, tell me this, guys. What is the one piece of information that what's really the one thing you need to calculate a pH? What do you need? The concentration of H plus. Fine. Well, H plus and H3O plus represent the same thing, right? Nod your heads. Okay. Pick up your calculators. Do this addition, please. 0.0683 plus 8, right here, 8 times 10 to the negative 8th, because that's what X is. Put that in your calculators and hit enter. Okay, so 0.06830008, right? That is the molarity of H plus. Okay, now, how do you get a pH from your H plus concentration? What do you do?
Negative log.
Negative log it. Okay, negative log, second answer, enter. What's your pH?
1.161.
Round that to 2 decimal places, please.
1.17.
People, that's the same pH. Okay, so did we really have to do that whole second calculation if we were just going to get the same answer? No, is the answer. Now, that's why I'm not going to make you, and I don't think the AP exam would expect you to do all of this calculation either, because your answer is going to be the same. But guys, I want to make sure that you have got this. Just because my answer is the same, does that mean that this reaction never happened?
No.
It did happen. But how come we can't see that it happened? It's so small. Does this reaction happen? Yes. Does it go in the forward direction a lot? No. So did my hydrogen ion concentration increase? Yes, but by such a small amount that you should feel confident calculating the pH at the end of a first dissociation, you're going to have the same pH. Okay? I just wanted to prove that to you. I don't ever want you to listen to something I say and just blindly, obey. Yes, she said it. It must be true. No, I want to prove it to you. All right? Okay. Guys, we are going to completely change gears here. We are no longer going to be talking about acids and bases isolated. We're going to talk about salts. What do I mean by the word salt? I don't mean table salt. An ionic compound. You got it. A metal and a nonmetal. A cation and an anion. You may or may not be aware, but when you dissolve ionic compounds in water, that simple act of dissolving them can cause the pH to change. Now, we know the pH of water is 7. Okay? The simple act of dissolving a salt in water, that can cause the pH to drop and become acidic. It can sometimes leave the pH right at 7 and it doesn't change. Other salts, you dissolve them and the pH rises and it creates a basic solution. Here is what you will be able to do, maybe not by the end of today, but certainly by the end of next class. You're going to have a superpower that only those inside this room are going to think is a superpower. Anybody else outside this room is going to think that, yeah, great. That's wonderful that you can do that. Here's what you'll be able to do. I will be able to give you any ionic compound I could possibly think of. And just by looking at it, no numbers, no nothing, by looking at it, you will be able to tell me, yes, that's an acidic salt. That's a neutral salt. That's a basic salt. Wow. Yeah, get your capes ready, everybody. All right? I know, what a nerd thing to say. All right. So what I'm going to try to do is to model for you the thought process, okay? And we're going to start, don't write this down yet. Let's just go through the thought process. We're going to start with our first salt. We're going to use just table salt, sodium chloride. All right? And what I do when I'm presented with a salt, just this is my habit, I always draw a line splitting the cation and the anion. Okay? If we put sodium chloride in water, it'll dissolve, yes? Do we agree? Okay. What happens when a salt dissolves? Like, what are you actually creating? What are these two pieces? The ions, yeah. Okay, so if I were to list out my major species, I would have Na plus, Cl minus, and water, which I'm going to write as HOH. You don't have to. It helps my thought process. And guys, our job here is to look at these ions and figure out which one will react, if any of them. Right? Let's start off with the sodium ion. Right? If that were to react with the water, I want you to think of water as like, don't think of it as H2O. Think of it as hydrogen hydroxide. Like hydrogen ion joined to a hydroxide ion. Think of it that way. If sodium were going to pair up with one of these pieces, which piece could it possibly pair up with? The hydroxide. Okay, so I would get sodium hydroxide. Oops. And what would be left? Just H plus, yeah. Okay. So this is a possible reaction that could occur. Here's how we're going to decide whether it does actually happen or not. Look at this product right here. Acid, base, salt, what is this? It's a base. Is it a strong base?
Yes.
Yes. It's a group 1 hydroxide. Okay, so this is a strong base. Guys, what does it mean to be strong? Completely ionizes, completely separates. Let me say that to you another way. Strong compounds are compounds that do not like to be together. They like to be apart. All right? So, look at this reaction. What are we doing? We are causing this compound to form. Does NaOH like that? No. NaOH does not want to form. It wants to be dissociated. So, guess what? This reaction, not going to happen. This ion is not going to react. What do you call an ion that just floats around and it doesn't react with anything? Yeah, spectator. This is a spectator ion. It doesn't do anything. Okay. So that didn't work out. Let's try the other ion. Let's try the cation. Maybe we'll have better luck there. If Cl minus were going to link up with some part of this water, which part would it be? The hydrogen. And what would that create? HCl. And we'd have just OH minus left over. Let's go through that same thought process. What is this? It's one of our strong acids. Do strong acids like to form? No. strong things dissociate. This is not going to happen either. Neither one of these ions is going to react. So, that, ladies and gentlemen, is a situation where the pH will remain unchanged. We would call this a neutral salt. Okay. When you dissolve table salt in water, if you add salt to anything that you are eating, and most things that we eat have some water in them, you can rest assured that the pH of whatever you're eating is going to stay right at 7. Okay? The way that I do this kind of more quickly than that, writing out those reactions, is what I do is I think this. The cation of your salt. Cations always form possible bases. Your anions always form possible acids. Anion acid, AA. Okay. So here's a little bit of the quicker thought process. What was the base that this one possibly could have formed? Which base was it? NaOH. And we said that was strong, right? So I'm going to put a little S above that for strong. Anions form acids. What acid was it that this could have formed? HCl, also strong. Guys, when you have a strong combination, neutral salt. Okay. That's a little bit of the faster way to think of it. Okay. Let's look at this other example. Potassium nitrate. Look at the cation first. What possible base could that cation form? KOH. Strong or weak? Strong. Put a little S. What possible acid could this form? HNO3, what is that by name? Nitric. Strong or weak? Imagine a perfectly clear, breezy summer. Nitric. Strong. So yeah, that's another neutral salt. Okay. So strong, neutral salt. What if it's not strong? We'll do sodium fluoride. Okay? Again, just because it's my habit, I like to separate the salt. All right, here are my major species. Na+, F-, and water. Okay? So let's go through that thought process. Start with the cation. Cations form possible bases. What possible base? NaOH. Strong or weak? Strong. I'm going to put a little S above it. Now, if it forms something strong, what does it mean about that ion? Will it react? No. So this is a what kind of ion? Spectator. It's not going to do anything. Let's look at the anion. What possible acid could that anion form? HF, hydrofluoric. Strong or weak? Weak. So I'm going to put a little W. All right. So let's think of that possible reaction. And you guys said it would form HF. And what would be my other product? OH-. Okay. Let's figure out if this is going to happen or not. You said this is weak, correct? You're right. What does it mean to be weak? Okay, what does it mean for an acid to be weak? Let's not get personal here. Okay? What does that mean? It does not dissociate, hardly at all. Let me say that to you another way. A weak acid is an acid that prefers to stay together. It doesn't like to be apart. Okay? This is a terrible analogy, but if you're a weak person, then you're going to need other people to be bonded to. If you're a strong person, you're independent. You're like, yeah, I don't need anybody else. I'm separate. Okay? Weak people need to stay with other people. All right? We don't need to get personal. We don't need to get personal. Okay? If weak things like to be together, like they prefer to stay as a whole unit, is this reaction going to happen? Yes. All right? So, if this happens, okay, look at what our other product is. Look at what we're making. We're going to be creating OH minus. If you're making a bunch of OH minus floating around in this beaker, where do you think the pH is going to end up? In the basic range. This is a basic salt. If I took sodium fluoride and dissolved it in a beaker of water and monitored the pH as this dissolving process happens, I would see the pH start to climb above 7 as that happens. Okay? So you could, just by looking at this, strong, weak, you could say to me, that's a basic salt. Do you think I'm going to ask you to calculate what kind of pHs these salts have? Yeah, I am. Okay. Now, I realize I haven't given you any numbers here, but if this is an acid, what is this? I mean, what is this thing doing from left to right? What is that? Is it an acid? Is it a base? What is it? It's a base. What is it doing? It's accepting a hydrogen. Is this one of our strong bases? No, definitely not. It's a weak base. How do you deal with weak base calculations? You do an ice table. I know you love it. I know you're excited. Now, again, I haven't given you any numbers, so let me just really quickly show you what that might look like. Okay, like I've given you some blah, 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 initial molarity. We don't care about water. Tell me, guys, when I get down to the bottom of this ice table, does anybody want to guess? I mean, you got a 50-50 shot. What kind of K would I need here? KA or a KB? Why do you say KB? You're right. Because it's a base. You got it. Now, you guys have not really had to guess which kind of K you needed, because in all these other problems, you just used whatever K value was given to you. So you didn't really have to think about it. Now you do. Because in a problem like this, guys, I might give you the KB, but I might give you something else. Because I'm just a big jerk and I like to make your lives difficult. Maybe I don't give you the KB for F minus. Maybe I give you this. I give you that. And I know what you're thinking. Well, that's really helpful, Miss G. That's like completely not what I need. Oh, but wait, my children. There is a wonderful equation right here on your equation sheet. Look at where it says KW. Find it. And look one line below it. Do you see an equation that looks like this? Not plus. Do you see that? Okay. Do you all agree? If this is an acid, that is its conjugate base. Would you agree? If you have the Ka for an acid, you can find the Kb that we apparently need by using this equation. Do you remember what Kw is? It's a constant. It's equal to a number. What number? 1 times 10 to the negative 14th. You can always get what you want. Okay? Here's the thing, though. Sometimes I'll give you the Kb that you need. Sometimes I give you the Ka that you need. You can no longer, or let me say it again. Sometimes I will give you the Ka that you don't need, but you'll use it. You can no longer, starting right now, you can no longer rely on me just giving you the proper K that you need. You have to think about it. Is this the right K value that I need? Don't make it harder than it is, everybody. Ask yourself what this thing being added to water, what is it? Is it a base? Is it an acid? This is a base, so I need a Kb. Okay? Don't make it harder on yourself than you need to. Okay? Let's look at an example problem. Okay? And by the way, if you want to see the, like, mathematically why this is true, there's a proof worked out in our textbook, and I'm not going through it. If you want that, then go look it up. Okay. This is our last task for the day. We're going to do this problem together. It says, sodium azide. This is the salt that we are dealing with. And guys, azide, that may be an ion you are not familiar with. Okay? I just want to make sure you all understand this is not sodium nitride. That would have this formula. Okay? Different compound. That's not what we're dealing with here. It says sodium azide is sometimes added to water to kill bacteria. Fun fact, this is also the starting reactant for the reaction that happens to inflate the airbag in your steering column in your car. Okay? This is where the nitrogen gas that inflates an airbag comes from. Just a little fun fact. Okay, it says calculate the concentration of all species in a 0.010 molar solution of sodium azide, and then I'm given some other information. What do you think I should do first? What have we done? Every time I've given a salt, I've been given a salt and I separate it, what do I do? What do I write out first? Major species, sounds good. This is what the azide ion looks like. All 3 nitrogens together have a -1 charge. That's a little unusual. Let's figure out which part of this salt is going to react, if any of it. What should I put above this sodium? S for strong or W for weak? S for strong, because it forms a strong base, which means that's not going to react. That's not going to happen. How about this guy? Azide. Okay. Remember, the thought process is, what acid could this form? Well, guys, if it's an acid and you're like, I don't really know what acid that is. If it's an acid you're not familiar with, what kind of acid do you think it is? It's weak. Because we know our strong acids very well, right? Of course we do. Don't be silly. Okay? As weird as it sounds to say this, the weak side of your salt is the side that will react. Okay? The weak side of the salt is the side that will react. So here we go. Let's write our reaction. think about predicting products. The anion forms an acid, which means this must be a base. What do bases do? They accept a hydrogen. Can you tell me what then the formula would be? HN3. And what am I left with? You got it. Without doing any math whatsoever, look at that final product I just wrote. Where should a pH end up? In the basic range. That's a good way for you to answer that question. Does my answer make sense? Okay. I need some molarities. Let's go back to the problem. Where is this azide coming from? It's coming from the salt, which I am told has this molarity. Guys, there's only one azide ion in that salt, so I can use that molarity. Was I given molarities of either one of these in the problem? Which means what about their initial values? 0. Okay. Keep going. What kind of K do I need here? KB, how'd you know that? Okay, you can answer it in two ways. You could either say, my reactant is a base, which it is, or you could say, because I'm producing hydroxide, I know I need a KB value. Did I give you a KB value? No, because I'm a big jerk. I gave you a Ka that you don't need, but you can get it, right? Using that equation. Can you graph now? Yeah, go for it. Anybody else get that for X?
Yeah.
Okay.
Wait, no, I got you.
Close enough. Close enough. Close enough. This is what we were supposed to solve for. The problem said, solve for the concentration of all species. All species, guys, just means anything left on this last line. Do I have azide ion left? Yes, I do. Let's just plug in the number. Do this subtraction. Tell me what you get if you round to 2 sig figs. This minus that number. Tell me what you get. Yeah. You get the same answer. Just because I got the same answer, does that mean that this reaction never happened?
No.
It did, but barely. Okay? These two guys have the same value, and they're just equal to what I got for X. So now I'll round for sig figs. Okay? Now I'm going to have you go one step further, even though the problem didn't ask for this. I want the pH. Now, we found X, yeah? X is my OH minus concentration. What do you think's easier to find before pH? Okay, the POH? Somebody give me a number when you get it. 5 point something. 6 what? 4? Okay. How do you change a POH into a pH? Subtract it from 14. What do you think I'm going to ask?
Does it make sense?
Does it?
Yes.
Yeah, it should be basic. Now, the last thing that I want to say, guys, is, does it make sense? Yes, it's a basic pH. Is it like super duper basic? No. Your basic salts, you're not going to get pHs like 12, 13. You'll get pHs in the basic range, but they're going to be a little bit closer to 7 than, say, a weak base and certainly a strong base. Same will go for acids, but we'll get to that next class. Okay? So we've done basic salts today. We will start next class talking about acidic salts, which really is not a totally different process. It's just one slight little difference. So we're done for today, ladies and gentlemen.